Okay, so in this video, we complete section 8.1, where we're talking about mean or p-tests for means and proportions of one population. Okay, so why don't you pause, copy, and play. So in the last video, we talked about p-tests for means. Now we're going to talk about p-tests for proportions. All right, so this is proportions of success. So since it's proportions of success, we have this notion that we're coming from a binomial population. Either successes happened on each trial or failure, right? So let's say we ran n trials, probability of success p each time, and x was the total number of successes. So x is going to be binomially distributed. And suppose that we actually run this once and we observe little x number of successes that's observed. And we'd like to test proportion. We'd like to test H0, our null hypothesis is that our proportion is equal to some value p sub 0. Alternate hypothesis is it's not, okay? And in order to test this, what we're going to do is we're going to look at how large or small our observed value is. So in a binomial distribution, n times p is the expected number of successes. And if the null hypothesis has p being p sub 0, then n times p sub 0 is how many successes you expect. So if x happens to be greater than n times p0, we're going to calculate the probability that we could be more extreme than x, which would mean even larger, since x is already larger than normal. But if x is less than or equal to n times p0, if it's less than we would expect or equal to what we expect, we're going to calculate the probability that our random variable can be less than or equal to that observed value. That would be the more extreme side of it, less than, okay? Whichever one of those two we do, for a two-sided p-test, we're going to double that probability to obtain our p-value, okay? If we only had a one-sided p-value, p-test or p-value, so if we had p greater than p sub 0 or p less than p sub 0, we wouldn't double it, okay? All right, and note, to calculate either one of these, what we're doing is we're doing a binomial distribution. So if I want the probability that my random binomial variable is greater than or equal to some little x, I'm going to start with I equaling little x and going all the way to n and running the PMF, or the binomial PMF through it. So this would be the probability of x successes, x plus 1 successes, x plus 2 successes, all the way up to n successes added together. And that can be very tedious, but R will make it very easy. So, for example, it turns out that about 13% of the population is left-handed. So let's say we have a sample of 200 people, and we ask them to raise their hand if they're left-handed, and 36 of them do. So 36 of them are left-handed. And we might ask, okay, is this sample unusually left-handed, like unusually more so or unusually less so left-handed? Do they not behave as the normal as the overall population does in terms of left-handedness? Okay. So our null hypothesis would be that no, this group is the same as any other group. Probability left-handedness is 0.13. Alternate hypothesis says, well, no, there's something different. It's not 0.13. Okay. Well, right. Well, let's check. So let's check n times p sub 0. So 200 times 0.13 is 26. And we've observed 36 left-handed people. So we've observed a high number of left-handedness. So we're going to calculate what's the probability that we could, a binomial distribution could be 36 or higher if the p-value is 0.13. That's the more extreme part of this p-value question. So we're going to calculate the probability that our binomial random variable can be greater than or equal to 36. So this means I'm going to test, I'm going to add up the probabilities of 36, 37, 38, 39, up to 200 successes. And here's the binomial PMF for I successes, all right? Now, that's way too much work. So I'm going to hand it off to R. And in red is the R command. D, which somehow means sum it on up. D binom 36 colon 200. So from 36 to 200 out of 200 trials with probability success in each trial 0.13. Okay, that would be the R command, and it spat out 0.0267. Now I've got a two-sided alternate hypothesis, so I'm going to double that output, and I get 0.0533. So that is the true p-value, okay? It's above 5%, so assuming we got a 95% threshold, we would say we fail to reject the null hypothesis, and we can't say that this group of 200 people is unusually left-handed versus the overall population. Okay. All right. Well, now let's try doing something we did in an earlier chapter with binomials, and we're going to use the same exact example. Okay. So why don't you pause, copy, and play? So in earlier examples, we sometimes said, well, the binomial computations are really tedious. Okay, they're not with R, but whatever. Back in the day, they were really tedious. And we could sometimes approximate this binomial distribution via a normal distribution, as long as we did a continuity correction. Okay, and that's what we're going to do here and observe something, I don't know, interesting, disturbing. Okay, so via the central limit theorem, under the null hypothesis, the sample proportion is approximately normal, with mu being that 13%, and the variance being the variance of the sample distribution, variance of, oops-a-daisy, of x over n. That's better. Variance of x over n. X is the number of successes divided by the number of trials. So that gives me the sample proportion, given by 1 over n times p times 1 minus p, right? Now, the variance of a binomial distribution is n times p times 1 minus p. But if I then divide by n, I have to factor 1 out of n squared out of the variance, which then simplifies 1 over n squared times the n, gives me the 1 over n, right? And in this case, I would get a 0.02378 squared as my variance, okay? All right, so I'm now going to set up that exact same p-value computation, but this time using a normal distribution approximation. So the probability that x is greater than or equal to 36 is approximately the probability that x is greater than or equal to 35.5. There's that continuity correction, treating each number like a bar that's 1 unit wide. So if I want to include the 36 bar, I got to go from 35.5 to 36.5 and start at 37 bar, et cetera, et cetera. I can divide both sides by 200, and that gives me my sample proportion. That gives me that guy. And this sample proportion is approximately normally distributed. So here's another approximation cropping in. The sample proportion is approximately normal. So I'm going to subtract the mean, divide by the standard deviation that we calculated up here on both sides. That gives me a z value on the left. And then using the tables or R, I get a p-value. Sorry, I get the probability of 0.022887. Since it was a two-sided alternate hypothesis, I double that and I get 0.0458. And now that is below the 5% threshold. So that would tell me I should reject the null hypothesis and conclude that this group of 200 is unusual in its left-handedness from the general population. So I've done two different computations of p-values here. And in one case, I accepted the null hypothesis or failed to reject it. And in this case, I rejected the null hypothesis. So I'm getting two contradictory answers. Please remember the first panel, that was the exact true p-value because I actually ran through the binomial computations to compute it. Here, I crapped out of the binomials and went with the normal approximation with the continuity correction. So this was an approximation, and it gave us a differing answer from the truth, okay? So that's a problem. And note, like in an earlier chapter, we said this normal approximation with continuity correction, you should feel happy using it as long as n times p and n times 1 minus p are both greater than 10. And they are in this case. So this old-fashioned rule of thumb, not very helpful. So with modern computing techniques and such, they've decided that it would be better to require that np and n1 minus p are both greater than 384 if you wish to reject the strictly binomial approach from the first panel and use a normal approximation here.